Suppose that we've got a problem that we want to solve. If we can write a formal specification of it, we can avoid a lot of misunderstandings when we try to describe it to other people. We may also be able to use automatic verification tools to prove that a proposed solution is in fact correct. So let's look at how we can use the language of predicate logic to do this. Suppose that we want to commission a piece of software to solve a problem. We need to describe two things. The preconditions. In other words, what relevant things can we be guaranteed are already true before the program starts? Any program we write can make use of those things without having to establish them. For example, suppose that we want to describe a program that looks up an entry in a directory. If we know that the directory is already in alphabetical order, that could be very useful. We can use binary search. We start in the middle and compare our element, say Cantor. Cantor comes before Euclid in the list, so we can immediately throw away all of the entries that come after it. But if the directory isn't sorted, that algorithm won't work. We'll have to look at all of the entries. Now, we also have to specify the post conditions. What has to be true when the program finishes in order that we'd be willing to declare that it has solved the problem? For example, suppose that we want to describe a sorting program whose job is to arrange the entries in a list in alphabetical order. Then we want to say that it will accept as input an arbitrary list, but we insist at the end that the list have two key properties. It has to be in order, and it has to contain all the same elements as the original list. We may also want to specify a third thing, useful invariants. Things that are true before the program starts and will remain true at every step along the way, with the possible exception of brief periods in the middle of individual steps. So, for example, in the case of our sorting program, we might want to say that it'll always be true that every list entry contains exactly one name. So far, we've stated our claims in English, but we know that that can be risky. So let's see how we can use logic to state our claims in a formal and unambiguous way. We'll use the Towers of Hanoi problem as an example. An instance of a Towers of Hanoi problem consists of 3 poles and a set of disks. To solve the problem, it's necessary to move all the disks from one pole to another. But any legal solution has to obey 3 key rules. The disks have to be moved one at a time. No disks can be on the ground or held in the air while another one is being moved. And you can't ever put a larger disk on top of a smaller one. So if we're going to formalize this, the first thing we have to do, as in any attempt to formalize, is to define an appropriate set of predicates. Let's do that. We're going to assert things that have to be true of disks and only disks. So we need to be able to say that something is a disk. We're going to assert things that have to be true of poles and only poles. So we need to say that something is a pole. We're going to talk about disks being on poles at particular points in time. So on of x, y, and t is true just if x is on y at time t. We need to be able to talk about disks being on top of each other, again, at particular time. So above of x, y, and t is true just in case x is above y on some pole at time t. And we need to talk about the relative sizes of our disks. So larger than xy is true just in case x is, in fact, larger than y. Okay, let's talk about preconditions. We'll assume that all the disks start out on pole 1 and are supposed to end up on pole 3. So we need to say that at time 1, every disk is on pole 1. How do we do that? Well, we know that we want to make a universal claim. So there you go, for all x. We know that our claim applies only to disks, so we need a guard that says that. So for all x, if x is a disk, then something has to be true. And now we can fill out the guts of the claim, namely that at time 1, every disk is actually on pole 1. Now let's think about whether there are any useful invariants. In other words, things that may be useful if we want to show an algorithm to solve the problem is actually correct. The rules tell us several things. At each time step, every disk is on some pole, and no large disk is on top of any smaller one. Let's encode those two things. Let's first say that at all times, every disk is on some pole. In other words, none are on the air or on the ground. How shall we start? Well, we know that we want to make a universal claim about times and disks. So let's write that. For all times and for all x. The claim only applies to disks. Other things don't have to be on poles. So we need a guard, which we can write by saying that being a disk implies something. Finally, we have to say what must be true of any disk. Well, there has to be a pole that it's on. So we write that. Next, let's say that no large disk is on top of a smaller one. It turns out that it's sometimes hard to encode negative claims of this sort. Often it's easier to state positive ones. So let's start by rephrasing our claim. We'll say that whenever one disk is on top of another, then it's smaller. By the way, it's not required that we do this transformation. It's just sometimes useful. All right, how shall we say this? Well, we know that we want our claim to be an invariant. In other words, it holds at all time steps. So let's start with that for all t. Next, we know that we want it to apply to all pairs of disks. So let's say that. For all x and y, if they're both disks, then something. Now, what we want to say is that if one disk is on top of another, the underneath one has to be larger. So let's say that. So if x and y are disks and x is above y, then y is larger than x. By the way, we could have said this using our original negative form, and it would have looked like this. There doesn't exist a time and a pair of disks such that x is above y and x is larger than y. It's often useful if we write individual invariants to combine them to make a single one that's the and of the individual ones. And so if we want, we can do that. We have that every disk is on some pole and no disk is on top of a smaller one. By the way, we might also want to mention that the difference between two time steps can be no more than one disk in a different place. We'll leave that for you to try. Now, of course, we also need the postcondition. What has to be true at the end if our algorithm has correctly solved the problem? But we'll also leave that to you.
Đông đi cày bừa, tía em đông đi cày bừa, má em là một người nông dân, tía em cũng là một người